Good morning, ladies and gentlemen. This is Jim Chastain with EasyPower, and we're going to have a abbreviated session this morning, specifically on what coordination, how it applies to arc flash results, and when it's important to coordinate, and some pointers in that direction and how the tools can help you do your job better. So one of the questions that comes up is, can I coordinate before arc flash calculations? And the answer is yes. In fact, all you really are required is a clean one-line diagram, and by that I mean the data that's required for the protective devices is been adequately completed in the one-line design, and with that you can do coordination. But in reality, as you're doing that, EasyPower will calculate arc flash in the background, and so it can be accomplished at the same time. It turns out coordination actually is very interactive with the rest of the system, and you can take benefit of that as you're doing the coordination. The other thing to understand is how that interaction takes place, and by modifying it or tuning it, you can actually improve the time for your study. Obviously, a poor design could be a serious threat to human safety, and the primary purpose of short-circuit analysis is to ensure that we understand what the worst-case arcing currents will be at any point in the system and identify problem areas that need to have attention in terms of mitigating the safety factor. The other thing I'd like to point out, though, is that coordination, the process of coordination, while it's very important in calculating arc flash and coordinating breakers, it also actually applies in other areas of system performance and in protecting equipment as well as human safety. One of the tools that's part of the coordination module is the sequence of events report and calculator. What I like to start with is the arc flash spreadsheet when we first complete the one-line diagram, and then go to the sequence of events calculator to kind of make sure I'm somewhere close as far as coordination. Typically, if you're doing a review on a system that has been properly designed and installed and not a lot of adjustments have been made to the protective devices, there's a very high probability that you will not have to necessarily make adjustments. On the other hand, if you have worked with a system that has people tweaking on it, then sequence of events and arc flash spreadsheet are just a start. In reality, you probably want to plot the curves to show really what's going on. So let's kind of jump into the tools and look at an example of exactly that situation. So here we have a one-line diagram. We've got the motors, heavy motors on the buses. Here's a 350 horsepower motor on a 480 volt bus. We have some protective devices upstream. As we go into short circuit and fault the buses, we can see that in this particular case, this is a bus that faults, and it's going to be taking a total of 42,000 amps. If we go and look at the arc flash spreadsheet and we go down and look at switchgear 2F, we can see that if that bus faults, the first upstream breaker to trip, and upon which the arc flash incident energy is calculated, is BL2FA, which is what we'd expect. The problem is, or the significance is, what if we really want to consider the impact or the utilization of BL2FC if in fact we're more concerned about a motor fault itself? So just a little point of interest, if the way the tool has been drawn, or the way the one-line diagram has been drawn, is to optimize and minimize the number of buses so that we don't have to use too large of a tool. On the other hand, if we're trying to really understand what's going on with the fault below this particular breaker, we may have to put in a virtual bus. And so what I'm going to do is disconnect this particular motor, go in and put a bus in between the motor and the breaker, even though there's physically not one. This allows us now to go back to the short circuit, fault this particular bus, and now see what the currents are actually through this particular breaker, specifically if there's a fault downstream of the breaker. So now this gives us a better idea if this bus faults, and we look at the arc flash spreadsheet. Sure enough, BL2FC is the trip breaker, and so that's what we wanted to see. So at first blush, we might think this system is coordinated, but just out of curiosity, let's go ahead and go into the coordination focus. Let's fault this particular bus, looking at the current, and then create a sequence of events by highlighting this particular icon, sequence of events. As we do that, we can see if this bus faults, this breaker will trip in 15 milliseconds, this breaker will trip in 50 milliseconds, this fuse will trip in 677 milliseconds, and as we go farther up, we see our relay is tripping in 125 milliseconds. So it's highlighted in red in that it's out of coordination. It trips actually between these two protective devices here. So something may or may not need to happen based upon what those particular set points are. So the only way to verify that is to go in and highlight, while we're in the coordination module, highlight those particular devices, the motor and a couple of the trip units and the relay, and then plot them. And here we see something fairly interesting, and granted I took liberties in setting it up, so obviously it wasn't properly designed to start with. And the reason I know that is here's the trip curve for my motor, here's the trip curve for BLF2A. Let's consolidate my one-line diagram here. BLF2A is actually the second breaker upstream, and we can see that it actually has a very likely probability of tripping as the motor executes a normal start. So what this is telling us is that although for an arc, so let's go back and fault this particular bus, and we see that we can put the arcing tick mark on there, that this is where worst case arc fault would happen, and there's obviously miscoordination between BLF2A and BL2FC, 2FA and 2FC, but more problematic is the fact that on any type of a normal start that has current in this area, there's a high probability that this breaker will trip in and of itself. So although it looks like the breakers are probably coordinated as maybe as well as these breakers would allow for an arc fault, they're really not coordinated for a normal operating procedure. And then if we look at our relay, we can see that it has a much quicker trip setting than the fuse, and that's why we got the miscoordination on the report, on a sequence of events reports. Okay, so at this point, what the engineer would want to do is essentially go through and complete a full protective device coordination on this particular leg, on this specific leg, and rather than take the time to do it all real time, because we're limited this morning on the webinar, I'm going to basically invoke Smart PDC to show how it can deal with this. All right, so you can see where we have some very obvious miscalibrated settings between the downstream breaker, the second breaker upstream, and then the relay. So apologize for taking the shortcut, but at this point it really does need, if you will, engineering work. It's more than just a review of the settings. We can see the settings are wrong, and so at that point we would want to have an engineer look at what the settings ought to be or analyze what the settings ought to be. And because our time is limited, I'm going to invoke Smart PDC, watch where my curves end up and the relay as I do this. All right, you can see it's made probably the biggest adjustments in BL2FC, but it's also raised the relay up, so now it's protecting more of the transformer, and we have what looks like a reasonably strong coordination, if not perfect. And to verify that, we can kind of go in and look at the auto coordination report. And now this will give us specifics on what was done and what's not done based upon the Smart PDC. So we see that the low voltage breaker 2FC was set up with these set points, and it's still having a little bit of a problem with the motor on the thermal damage. Here's it's telling us that we probably should have a motor overload specified in the starting circuit, which we do not. But now it's got set points for again the 2FC breaker upstream, and when we get to the one downstream, we see probably have these upside down, starting at the load. So it's doing the downstream one first. And then the one that I was curious about is looking at the relay. And so you can see now it's made some major adjustments on the relay, and it's still having an issue, as we observed, being able to protect the transformer, at least the way that's currently set up. Now, that's not to say that's necessarily a bad thing, that the engineer that designed the system may be fully aware that there's no potential based upon the full load current that we'll ever get to that point on a transformer. But at least we have a report verifying that we set the relay and the protective devices, and made note of that lack of coverage, which is essentially this area right here at the top. I take it back, it's this area right here at the bottom. All right, so that's the bottom line here with the focus on coordination. I apologize for starting early today. We will have a recorded version of this on the website by the end of the week. Other pre-recorded webinars are available at EasyPower.com, both in-depth on a technical basis and all of these refresher snippets as we go through the week. Appreciate your attention.